So we're lesson 4.4. First problem scenario is carbon dating. This is similar to problems we've done before, but there's two more properties of logarithms that we're going to see in this lesson that we haven't seen yet. We have this equation, A equals 0.8861 to the power t. Just want to think about that equation for a second. A equals 0.8861 to the power t. And what do A and T mean here? So looking back here, this is in a carbon dating for ancient artifacts. And if you look at the last second sentence, the fraction of the original carbon 14 remaining, right? So some organism is alive, it dies. It's got a lot of carbon 14 in it. That carbon changes form molecularly, atomically, from carbon 14 to carbon 12. And so when the individual dies, it has 100%. That would be just a 1 as a number, the fraction. And then over time, it loses carbon 14 into carbon 12. And so we'll look at the remaining fraction. T here, this is important. T is in thousands of years. So let's add that to our notes. So off to the side here, A is the fraction of carbon 14 remaining. Remaining, there we go. And T is thousands of years. Right, so in other words, T equals 1 really means 1,000. T equals 2 really means 2,000, and so on. Okay, so it's a slight twist on the way we've been using. Instead of T as the years after something, this is thousands of years that have gone by. So if we see T equals 10, that's 10,000 years. T equals 20 would be 20,000 years. T equals 100 would be 100,000 years, and so on. So it takes a while for the carbon to decay, but we can measure that. So if 1,000 years went by, if I made a table, one really is, if we had another column called years here, 1,000 years is T equals 1. If you plug a 1 in here, you get the base, 0.8861. If 2,000 years went by, T would be 2, and we'd have to say, okay, what's this to the power 2? So I need to ask a calculator about that. Right, and that's similar to what's going on here. They didn't ask about 1,000, they just asked about 2,000. So I'll jump to 4, 8, 6, and so on after that. So if I take 0.8861, get those digits right, 8861, yep. And I want to raise that to the power 2 and see what I get. I get 78517. How many decimal points do they want? Places? They want 3 decimal places, even though we started with 4. That's okay. So that would be 785. In other words, so if I die now, 2,000 years from now, if you dig me up and measure how much carbon 14 is in my body, you'll find that I have about 78.5% of what I started with 2,000 years later. You found me as like a mummy under my house. Interesting. 4,000 years later, T would be 4. Whoa, that's not a 4, that's a T. T would be 4. And so I'd have to take this to the power 4 on my calculator. This would be a good place for a spreadsheet, huh? So 0.8861 raised to the power 4 to 3 decimal places, 616 thousandths. 0.616. So if we found a 4,000-year-old cat mummy, we would expect it to have 61.6% of its carbon is carbon-14 and the rest is carbon-12. Right? So we can compare those two to get that ratio. So this is how archaeologists figure out how old things are. They dig something up, they take a sample of it, they look at how much carbon-14 is in there, how much carbon-12 is in there, and they look at the ratio of carbon-14 to the total carbon, and that gives them an estimate of how old something is. So they dig something up, they find there's, let's do a quick test here on a calculator. If I take 1 minus 0.616, so I dig something up, I measure, there's 61.6% carbon-14 and 38.4% carbon-12, then that would tell me this thing I dug up is about 4,000 years old, right? So they work it the other way. All right, so you need to fill out this table here with those numbers. I'll let you calculate the rest. So get those other two there. And remember, if the years is 6,000, T is 6 in your formula. Calculate those and we'll check out the next part. So here's my spreadsheet version, and I have the 2,000, 4,000, 6,000, 8,000 years later. And looking back here, okay, textbooks commonly report the half-life of carbon is 5,730 years. Based on your calculations, what do you think half-life means? Based on our calculations. Okay, let's see, based on our calculations, when do I have about half of what I started with? So up here, I'm at 100%. When am I closest to 50%? This is about 50% right there, which is about 6,000 years later. So around 6,000 years later, we have a little less than half. So somewhere before 6,000 years is where we should see exactly half. Now they claimed it was what, 5,730? So I'm just going to check here by typing 5,730. And then I'm going to fill my equation down here, which just says take that power to the t. Oh, we got to calculate t there. T is just to divide the years by 1,000. My formula says, yeah, look at that, 50% right there. Boom, nailed it. Okay, so half-life is the number of years that has to go by till you get half of what you started with. Let's write that down. Half-life. Number of years, in this case, length of time in general, to get half of what we started with. Now, if half-life is constant, like if it's always 5,730 years, then what I should see in my calculation is that if I go another 5,730 years, so that would be almost 12,000 years later, I should have half of a half, which is a quarter. Let's test that out. Does that make sense, right? So I go another 5,730 years later. So let's see, what is 2 times that? Equals 2 times 5,730. So if I go 11,460 years later, I should have half of a half. Let's calculate. So I'm going to fill my 2 formulas down here. And there's, hey, look at that, half of a half, 0.25. Cool. I think I'll share this out in case anybody wants a copy of it. If you don't, just ignore it. this in the video also. Comments or description, copy, done. Chat, video. All right, in case you want to copy this, you would then have to log into Google and then say, make a copy so you can play with it. Otherwise, you're just watching me play with it. All right, so then we have to choose the best answer here. So I'm gonna let you read through your answers for a minute. They won't be in exactly the same order as mine. All right, so let's troubleshoot this. Let's see, my first one says carbon-14 has a total life of 11,460 years. And I went to my spreadsheet to play with that, and no, it's still got some life left. There's still some carbon-14 hanging out there. It ain't all gone. Okay, so my spreadsheet says, no, that one's out. Okay, let's see, what about the next one? The amount of carbon-14 remaining decreases by half in 5,730 years. Yeah, my spreadsheet definitely verified that. Then after another 5,730 years, there will be half of that remaining. Half of a half is 0.25. My spreadsheet definitely, I'm pretty sure that's true according to my spreadsheet, but let's look at the other ones to make sure. After 5,730 years, half of the carbon-14's life will have passed, after which it will grow back. What? It's not no lizard growing back its tail. Okay, I got nothing, no evidence of that. That's crazy talk. All right, next one. The amount of carbon-14 will remaining decreases by half. It did decrease by half the first 5,730 years, then another 5,030, there'll be nothing left. Is that zero? That ain't zero. That's nonsense too. Okay, so number one, nonsense. Number two, or the fourth one says the same thing as the first one with more words, and number three is just crazy talk. Now yours will be in a different order, so read yours carefully. What we did find is every 5,730 years, we have half of what we started with. All right, I'm going to test that one more time on my spreadsheet. Check this out. All right, let's see. Let's pick on this 38% there, 38% left after 8,000 years. So from there, if I add 5,730 years to 8,000, I should get half of that 38%. What's half of 38? Let's see, half of 30 is 15. I think that would be 19%. Half of 38 is 19. Yeah, I think that's right. Okay, so I'm just going to add a new line down here and check it. So my claim equals, from the 8,000 years that already went by up there, I'm going to add another 5,730 years. And then if I fill my formulas down here, I think I'll get half of 38%. 0.38 as a decimal is 38%, right? Ooh, I get it right. Okay, yeah. So it doesn't matter what you started with. Wherever you're at, if 5,730 years go by, you get half of whatever you had before at wherever you were. Every 5,730 years, half of whatever you started with transforms. That's what we got. That was exciting. Moving along. Okay, what do we got here? 5,730. Okay, so that'll give me half of 1. That's 0.5. 11,460. Let's see. That's this one right here. That was that 2 half-lives. Half of a half is a quarter. Okay, so let's make a new table maybe to do this one. So it looks like, my guess is this is 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Let's check that out on a calculator. If that's the true, we should just keep cutting in half as we go down here. And the spreadsheet's a good way to go here. So here's my setup. I'm going to type in years. and then t, right? Because t is different. 1,000 years, t is 1. And then our carbon fraction. So I'm just going to call that carbon. All right. And then the years we want to look at are 0, and then 5,730. And then basically we just want to keep adding 5,730. So that's what, if you fill that, if you highlight those two and fill that down, that's exactly what will happen. It'll keep adding another 5,730. And you should see I get the same exact numbers that were listed here. If that seemed like some weird magic, then I'll do it this way. Starting with 0, I want to make a formula that takes whatever number I have above and adds 5,730. And then I just want to repeat that formula, which will just keep adding to whatever's above 5,730. So enter, click on only that cell, and then fill it down. Okay, and I only need to go that far. Okay, so what I've just determined is that these numbers here are all 5,730 apart. To get the t for my formula, I just take those numbers and divide by 1,000. So click on the first equals, click on the first one, divide by 1,000. Google will ask you if you want to fill down, and you can just say yes. Okay, so those are the powers, t, and then the formula is that 0.8861 raised to the power, that's that shift 6 key, and then click on the t value next to you. Enter, fill it down. Okay, so we got a little bit of rounding error going on here. So we're just going to knock that down to 3 decimal places. Does it say that to do that anywhere? Enter integer or decimal, but the problem above went 3 decimal places. So I'm just going to do that. So drop down decimal places, please. And 3 there. Okay, so let's see. Half. Yep. This should be half of a half or a quarter. This should be half of a half of a half or an eighth. And this one should be half of an eighth, which should be a 16th. I'm going to double check off to the side here. Right, I know 1/2 is 0.5. We know 1/4 is 0.25. My claim is this one right here is 1/8, half of a half of a half. So equals 1/8. Yep. And then the next one, no, I don't want to fill. This one should be half of an eighth would be a 16th. So this one should be 1/16, but rounded version of it. 0.0625 rounds to 0.063. Pretty close. If I added more decimals there, oops, here, I should probably see that it's pretty darn close. Yeah, 625, and then I have some rounding error due to my formula. Yep. So basically what I see here is starting with 1, we get 1/2, and then we get 1/4, and then we get 1/8. Oops. 1/8, and then we get 1/16. And you may be asking, why is he typing those quotes there, that apostrophe? And the reason is if I type 1/8, the computer is going to think that's January 8th, not the fraction 1/8. And the apostrophe tells it, knock it off. Okay, so back here, integer or decimal. So I need the fraction versions of these. So 0.25. Oops, I didn't mean to submit. 0.5 of a quarter is 0.125 on my spreadsheet. And then this one was 0.0625. It might take the rounded version. Submit that because I know that's right. A rounded version was 6.3. Oh, it'll take that too. 0.0625 is probably a better answer, but we'll do the rounded one. Okay, so what did we just determine here? That when I have an exponential function, the half-life is always the same number. Let's put that in the notes. So I had explanation, brief explanation of half-life here. Number of years or amount of time to get half of what you started with. And the other thing, we only have one example, so I really don't have proof of this, but with an exponential function, that decreases, right? Ours is going down over time. The half-life is always the same. In this case, the half-life was 5,730. For the car depreciation, it'll be a slightly different number. Okay. An artifact is found. Scientists determine that it contains 20% of its original carbon-14. So, right, they grab this thing, they scrape it, they take it to the lab, they say, okay, how much carbon-14 is in there? How much total carbon is in there? Okay, 20% of the carbon is carbon-14. How old is this thing? Let's figure it out. So now we get to do a little archaeological sleuthing. Okay, so we have the formula that the amount of carbon as a fraction is 0.8861 to the power t. And they said they just found 20%. 20% as a decimal is 0.2, right? 20 out of 100 reduces down to 0.2. So I need to solve this equation. When does 0.8861 to the power t equals 0.2? Now there's no multiples here, so I can just jump right to a logarithm. So I take the logarithm of each side, log of 0.8861 to the power t has to equal the log of 0.2. The t on this side pops out as a multiple. Now I just have this multiple of t. How do we get rid of multiples? This is just some number, so I can just divide by it. But I got to do the same thing to the other side. Now on this side, I have a number divided by itself, and a number divided by itself is always 1. On this side, there's not much I can do but plug into my calculator to figure out what t is. So we're going to find it and check it. Calculator, I'm going to go to Desmos this time. So I want to know, what is the log of 0.2 close parentheses divide by the log of 0.8861, and I get 13.3. Now that's t. What is t? Let's see, I wrote that down somewhere. There's my notes. T is thousands of years. So that's not just 13, it's 13,000 years would be my answer. I think if there's 20% carbon, 14 left, this thing must be over 13,000 years old. How much older? Well, around 13,300 years. I'm not sure about the 9 years there, maybe. All right, let's check it. To check it, we go to our formula, which says take 0.8861 and raise that to the power. In this case, the power is going to be about 13. So 13, let's go 13.3. And look, that's about 20%, 0.20. Pretty good. Let's see what kind of answer did this want here. How many years? Okay, is it 13 years or 13,000 years? 13,000. And if I'm careful about this, if I multiply that by 1,000, let's do that. Let's get rid of this line. Take that line above. There's a previous answer here. There it is. Take that times 1,000. right, then I get like 13,309 years roughly. Estimate the age of the artifacts using the previous problem. 13,309. Yippee. Okay. Using the previous problem, let's see. It's more than 11,000 here. So I might guess 12 or 13 based on just that number up there, but we were able to calculate it. Okay. Now here, oh, I guess I jumped ahead. I answered question number 5. Here they wanted me to solve the equation. Boom, done, 13,309. Nailed it.